This animation. So this is the last one.
So as I mentioned at the very beginning, the four of those are more pedagogical, but this is going to be somewhat like a colloquium style of the work which me and my group have been doing, which is on a particular way to think of putting together the principles of quantum theory and gravity. So let me begin with a statement. Let me begin with a statement which will be obvious to you once I make it, but you might not have thought of it like that. The statement is that if you have a glass of water, you could have discovered that the water is made of discrete structures like the atom and all its molecular dynamics, etc., without ever doing an experiment at angstrom scale. Because this is precisely what Boltzmann did. Boltzmann said that if you have water and you can heat it, then it must have microscopic degrees of freedom in which that heat can be stored. So if you look at the history of physics at that time, right from the days of cavemen, people knew what is the difference between a hot body and a cold body, but they did not know what this heat is. And there were very smart people who were going on wrong direction by thinking of heat as some kind of a calorific fluid which get transferred from hot body to cold body, etc., etc. And all this was cut short by Boltzmann, who said that heat is just a mechanical phenomenon. There has to be discrete structures, and these discrete structures hold the energy which you suffer. He in fact went further, and he said that you can even count how many such degrees are there. So if you know this energy and if you know the temperature, then the number of upward, here is where Boltzmann constant comes in, the number of discrete structures which you have is proportional to E by T. Now this is a very interesting formula. It's known to all of you, but you might not have seen it in this way. Normally you write it as E is equal to half K N V. If you write it like this, then the energy and temperature has thermodynamic limit. You think in terms of energy and you think in terms of temperature in thermodynamic limit. But this N has absolutely no meaning in the thermodynamics. N is the total number of discrete structures, and in the thermodynamic limit that is infinite. So this relation connects the microscopic physics and tells you that microscopic angstrom scale physics leaves a trace in a glass of water. The fact that you can heat the glass of water is because at angstrom scale there is microscopic. The reason this happens is because the Anderson statement that more is actually different. If you think of macroscopic physics, there is a new variable which comes in, which is the difference between energy and free energy. Energy exists in point classical mechanics and in normal mechanics of bodies, but the concept of free energy is not well defined for a single particle or a single molecule. In fact, concepts of pressure, temperature, etc., you cannot define it for a single molecule. So what is happening here is that when there is a lot of them, a new concept called free energy comes in, and the difference between these two is what we call the heat content, which is temperature times entropy. If you divide it with volume, you get essentially the heat density, which is the temperature multiplied by the entropy density. Now there is something called Gibbs-Duhem relation for zero chemical potential objects, which some of you might have learned, that this Ts is just P plus rho of the system, okay, for systems where all these quantities can be defined. And normal matter has a heat density. What we discovered over the last 5 decades or so is that the space-time behaves like a fluid. The space-time also has a heat density. Just as if I have a glass of water and that at any point inside at that body of water, I can associate an entropy density S and a temperature and therefore a heat density. You can also do that for space-time. At any point here near the Earth's surface, I can associate a temperature and entropy density with the geometry of the space-time, just as I can do it with a glass of water. Now this idea some of you would have heard in the context of, for example, black holes. Black holes has a temperature and an entropy. But this idea is much more general. That is why I said that near Earth's surface, here, right now, I can associate a temperature and entropy with this event in space-time. It also transcends Einstein gravity. As we will see, this idea is very general, and it is a very general way of thinking about geometry. And Einstein's equations and Einstein's gravity is just one way of talking about the geometrical evolution. Now, because the space-time is hot, Boltzmann tells us that it must have microstructure. And now I just want to overview what I am going to show you in detail later on, just to summarize. We will find that we can actually count the atoms of space-time without doing Planck scale experiments. That should not come as a surprise the way I have introduced this subject. I can count the number of gas atoms in terms of Avogadro number without ever doing angstrom scale experiment. People did this much before they knew what the gas is made of. In the same way, we don't today may understand what the space is made of. We don't know what the atoms of space are. However, we can count how many of them are there, just as in the case of a fluid. I will show you that how that comes about. And it also allows you to describe the evolution of space-time, which is normally described in terms of Einstein's equations as a geometrical thing in a completely thermodynamic language. You can obtain it from a thermodynamic extremum principle. You don't need an action principle, you can extremize the thermodynamic equation. This field equation therefore has the same conceptual status as equations of fluid mechanics. In fact, this was my main misgiving about all approaches to standard quantum gravity, like string theory, loop quantum gravity, etc. They seem to think that because the metric satisfies a differential equation called Einstein's equation, you should go and quantize the metric. This is like saying that if I take fluid mechanics, the velocity field of the fluid mechanics or a displacement field of a fluid mechanics is going to satisfy a differential equation, and I should go and quantize that. If you quantize that, I will not get the molecular structure of the fluid. At best, if you do it for a solid, you will get phonons, but you won't get the quantum structure of the atom. So in the same way, this is not the route to follow. You don't think of metric as some kind of a fundamental variable and apply quantum laws to it. You have to approach it in a very different way. There is also this deep question of why. Why is it that gravity has this thermodynamic behavior? I mean, we know gravity is special and it's different from other interactions, etc. But still one would like to know why this happens. How can we understand this both macroscopically and microscopically? So let me explain for a minute what I mean by why, by giving an analogy. Suppose I take a 5 kilogram ball and a 1 kilogram ball and I drop it. Then I know that both of them are going to hit the ground at the same time. This is known since the time of Galileo. And you can ask why. Why does it fall at the same time? Now one way to answer this is to say that the inertial mass is equal to the gravitational mass. So when you write down the Newton's laws of motion, that those two terms cancel out and all the particles fall with the same acceleration. And then you say you shut up and inertial mass happens to be equal to gravitational mass, don't ask any further questions. But we do know today that there is a deeper level of answer to this why. What we think of is that gravity is not a force acting on masses. Gravity is just the curvature of the space-time. Particles follow a geodesic in the curved geometry. A geodesic in the curved geometry doesn't care about the mass of the particle. So if particles follow a geodesic, then all the particles, irrespective of their properties, has to follow that geodesic. So there is a much nicer way of understanding this from a deeper layer. That is what we are looking for. One can easily take a particular space-time and then do the quantum fields in that space-time, obtain temperature, entropy, etc., and say that is it. But this connection between temperature or entropy with gravity is very superfluous, and we are looking for a much deeper connection. I will tell you that the reason for this is very deep, and it connects two things which people thought was completely different. I will show that if gravity has to be immune to the zero level of energy, that is when you shift the overall zero level of energy by a constant, gravity should not care about it. If this holds, then I can show that it must have a thermodynamic. Now these two concepts, both of them are known in literature, but nobody thought that these two are interrelated. The shifting of the zero level of energy is usually talked about in the context of cosmological constant problem, because addition of a cosmological constant essentially does that. And the thermodynamics is usually talked about in the context of horizons and black holes, etc. What I will point out that these two features, which are usually thought to be completely separate, are actually one and the same. So once you do that, you will find that the macroscopic field equations arise from extremizing what I call heat density. So there is a heat density for matter, which is T times S, and then we will write down a heat density for gravity and you integrate that over a null surface. This is the heat density of that particular null surface. You maximize the heat density of all the null surfaces simultaneously and you will get the field equations of gravity. So this is just the extremum principle of thermodynamics. Instead of entropy density, you are extremizing the heat density. This works for a very wide class of theories, and the form of Hg decides whether you are talking about Einstein's theory or a more general class. So this is a very general description of the dynamics of space. In this description, the time evolution of the space-time has a very holographic aura to it. You can define some surface degrees of freedom in a region, you can define some bulk degrees of freedom in a region, and the difference between the surface and bulk degrees of freedom will drive the time evolution of the space-time. So I call this a departure from holographic equipartition. That term will become clearer as I go further. And if there is no time evolution, n surface is equal to n bulk. So you also have a very beautiful result that in any geometry, any static geometry, I can define certain surface degrees of freedom and a bulk degrees of freedom, and the surface and the bulk degrees of freedom are equal in number if the geometry is static. So this this is very much like the holography which you hear about, but it is used in a different sense from string theory, because in a string theory there is a very precise notion. Here what we are doing is that we are going to define these two things in the gravity sector and matter sector, and their equality is what tells you that the space-time geometry is static. And you can obtain all these results without actually tying yourself down to any specific model of quantum gravity. The other feature about this approach is that the heat density is P plus rho. Gravity is tuned and responds to this heat density and not to energy density. Normally you think of gravity responding to energy, but it actually responds to heat. And this particular object vanishes for a cosmological constant. Some of you would know that the cosmological constant has an equation of state P is equal to minus rho. So P plus rho is 0. Cosmological constant doesn't have entropy. So gravity doesn't care about it. And in this approach, cosmological constant actually arises as an integration. Its value you can actually determine by a new conserved quantity in the universe. So this approach actually tells you what is the numerical value of the cosmological constant. That was a major achievement of this approach, which there is no other model which can actually do that. So I will emphasize it right at the end. Okay, now let us go further. This is all at the macroscopic level. How do you tie it up with the microscopic structure of space-time? At the microscopic level, you think of some atoms of space, and these atoms of space should have a distribution function, and that is what leads to this variational principle. How many atoms of space are there from that? And that comes from a very peculiar result, which I will explain. Then if you take this space-time, which has quantum corrections to it, it turns out that to each event, you can attribute zero volume but finite area. Normally if I ask you what is the volume associated with this point, you will say it is zero. Length, area, volume, everything associated with a single point is zero. When you introduce discrete structure in space-time, like Planck length, etc., it turns out that the length is irrelevant, the volume associated with a point is still zero, but the area associated with a point picks up a finite value. And this comes about because of some very peculiar geometrical features which I will illustrate, and from this you can apply this. Okay, now let us get on with the details. So this is some kind of a preview, and now let me do the details. So we want to build a theory for gravity based on these principles. First, we need to understand the distinction between the kinematics of gravity and the dynamics of the gravity. The kinematics of the gravity is based on the principle of equivalence, and that is what makes gravity so beautiful and elegant. the dynamics does not have, in the conventional way, any elegant principle. I mean, you cannot write down an elegant principle like principle of equivalence and obtain the field equation. Okay. What we will do is to supply a fundamental principle for dynamics as well. So in order to do the kinematics first, let us go to some event in space-time. So this is time, this is space, and this is an event. And these are the light rays emanating from this event. These light rays are not 45 degrees because we are using some curved space-time, some generic coordinates. Now, if you go to the freely falling frame at the same event, this is lowercase t and x to uppercase t and x. At that point, the light rays become 45 degree lines. Okay, that is what freely falling frames do. And there is a region in which the freely falling frame is applicable. And outside, of course, light rays will go in any case. If I claim that the special relativity should hold in this freely falling frame, it immediately tells you how gravity affects matter. So all of gravitational influences on the matter, the kinematic, can be obtained from just this principle of equivalence and the validity of special relativity. Here, for our purpose, we will assume that matter is described by a symmetric energy momentum tensor and its divergence equal to 0 tells you its equations of motion. The second important point which comes about when we look at this coordinate transformation is that you now have to take into account all observers at a equal status. This is what general Gravitation tells you. Once you do that, you can have observers who will find that regions of space-time are inaccessible to them. And this can happen in any space-time, including flat space-time. So normally again one thinks of this in the black hole context. If you have a black hole, there is a region inside the black hole which is inaccessible to observers also. This is a very observer dependent statement which is not often realized. There is nothing absolute about a black hole. If I have another observer who is falling into the black hole, he will have access to more information than a guy who is sitting outside. So the lack of information because there is a horizon is because you think of only observers who are outside. So in the same sort of way, and so there are observers in the short scale space-time, in the black hole space-time, who have different levels of accessibility to the information. So in the same way, even in flat space-time, if I have two different observers, they might have different amounts of accessibility. This tells you that you have to take this idea of non-inertial frames very seriously. It is not just some coordinate relabeling. We have to think of it as fundamental. This in fact has been done, and when you do that, you obtain a result which I personally consider is the most beautiful result which we have in putting together principles of quantum mechanics and gravity. What this result tells you is that if you have an observer in any space-time who has a horizon so that beyond that I cannot see, it is like standing in a beach and you have a horizon which limits your vision. If there is a horizon for that observer, then he will immediately think of the space-time as being hot. And he will attribute a temperature T to the space-time, which is essentially related to his acceleration, which can be traded off for other geometrical quantities in various contexts. So there is a temperature to this space-time, but this temperature is completely independent of the field equations of the theory. So you start with the geometry. That geometry could have come because of, in a particular theory, it is a solution to the field equation. There could be another theory in which also this is the solution to the field equation. So the dynamics is very different. But once you have given me this metric, I can compute this temperature. So the temperature is purely kinematic.
This temperature is observer dependent.
This is observer dependent. Even the temperature of a black hole is observer dependent. Because if a guy is falling freely into this thing, all temperatures which we attribute to the horizon depends on the observer. This will also depend on the observer. So the observer has an acceleration and the observer perceives a horizon. If he doesn't perceive a horizon, he will attribute zero temperature. So it is the perception of the horizon which gives him a thermodynamic tint. Now that is completely independent of the field equations of the theory. And this is, if you think about the analogy, you should keep in mind that space-time is like a fluid. Now if you take a different fluid, you can always keep all of them at the same temperature. You can even take a metal rod and a glass of milk and keep it at the same temperature. So saying something has a given temperature doesn't tell you anything about the structure. So in the same way, spacetimes can be at the same temperature, but we will not know the dynamics of the spacetime. For that you need entropic information, which we will come to. So here is an example. This is a standard example. This is called a Rindler observer, uniformly accelerated observer. We discussed a little bit of it yesterday. And he has a horizon, and he will attribute a temperature to this horizon. There is a local version of the same effect. So you go to this event and you have this freely falling frame with this 45-degree light phase. You can also have an observer who is sitting quietly there. That guy will have a trajectory which is sort of straddles this, just like this trajectory, but in a local way along this. And he will again attribute the same kind of a temperature. What happens is the following: you have this freely falling frame with a freely falling observer, and you have an observer who is sitting quietly. The vacuum fluctuations which this observer attributes to this region for a quantum field, for example, will translate as thermal fluctuations as viewed by. This is a very non-trivial equivalent, but I won't go into the details of that. But this happens. As a result of which, in any local region, there is a natural way in which, given this observer, I can attribute a temperature to any null surface. So you take any null surface in the space-time. There are observers who perceive that null surface as a horizon, and they will attribute a temperature. It also,
the definition of the vacuum will be different.
the definition of the vacuum for both these guys will be different, and that is, in fact, what is vacuum here will look like a thermal state.
What that means?
That is why he has a temperature, and that temperature will now depend on H cross by C. So quantum mechanics has come. The temperature is a purely quantum effect in this subject.
When you said that the sky is quiet, that means he's actually
Accelerating with respect to the freely falling frame. Yeah, but this is exactly what happens in, you are sitting in a chair, but there is a freely falling frame here in which he will not feel the gravity of the earth, while you are feeling the gravity of the earth. So with respect to the inertial observer, you are accelerating. Okay, that is what happens. Okay, now there are two results related to this local Rindler observer which we are going to need for later, so I am going to describe them. First is that if you take this observer and if there is some matter which crosses this horizon, he is sitting in this trajectory, but there could be another trajectory of matter which crosses this null surface. So since he has associated a temperature with that null surface, it is like having a heat engine at some particular temperature and dumping energy to it. So you are essentially dumping entropy, or there is a heat which is transferred, the thermalized heat which is transferred onto this null surface. And you can find an expression for that. This you can actually derive. This was one of the key contributions from Ted Jacobson. That heat is given by TAB, LA, LB. TAB is the matter energy momentum tensor. LA is the null normal to the null surface. So the heat density of matter, as it crosses a null surface, the heat density contributed to the null surface by the matter is just TAB, LA. The second result is that if you look at a horizon, that is t is x is equal to plus or minus t, which is same as x square minus t square equals 0. If I now go to the Euclidean space-time where your t becomes I times t, you will get this to be x square plus t square equal to 0, which is just the origin. So the entire null surface collapses to a origin in the Euclidean plane. So here is a picture. This is the space-time diagram in the Minkowski plane. This is the Rindler observer, and this wedge-shaped region here, pink region, will translate into a circular region when you go to the Euclidean line. What is happening here is that this particular curve is given by sin x and cos x, and when you change t to it, that will become sin and cos, which is a circular curve, and this internal region is going to go into this. In particular, this x square minus t square equal to 0, which are these two red lines, is going to collapse into a single point. This is important because it tells you that if I do anything in the Euclidean space, if I take 2 points in the Euclidean space and I take that point approach the origin, what I am doing here is to approach the null surface. So null surfaces will get picked up when you move towards the origin in the Euclidean plane, and that is something which we will come back to. Okay. Now I want to do dynamics. And I lamented that dynamics does not have a gating principle, so I am going to supply a gating principle. So the principle is exactly something which we translate from matter section. We know that the normal matter equations of motion do not change when you add a constant to the Lagrangian. After all, it is only the derivative that is Lagrangian which appear in the equations of motion. So I can add a constant and nothing. So I claim that gravity must respect this symmetry. So I postulate that. So this is the key postulate of the new approach. So we want to have this symmetry preserved by gravity. What it means is that the variational principle I use to obtain the dynamics of space-time should be invariant. When I add a constant to a Lagrangian, it is equivalent to taking the energy momentum tensor of matter and adding to it a unit matrix with a constant here. Okay, this is what we do. And when you do that, your gravitational field equation should not change. This turns out to be an extremely powerful principle. The first thing it tells you is that you cannot use metric as a dynamical variable if this has to be true. It is actually fairly elementary to see. It's like a theorem, and the way you show this is that if the matter Lagrangian or matter action is an integral of a matter Lagrangian over a 4 volume, then you will have a L matter multiplied by square root of minus G in your theory. So if I add a constant to the L matter, it will go and couple to both sides. So if you are going to vary the metric, then this invariance will not go. So you cannot have G mu nu as the dynamic variable. That creates a problem. So that is what I said about that. The point is that
I mean, this has to be invariant under this. TAB is a stress tensor.
Yeah, it is a stress tensor of matter.
So you just shift the stress tensor.
You add a constant to the Lagrangian. If you add a constant to a Lagrangian, stress tensor will automatically shift like this. And that is what it will pick up. So the variational principle which I am going to now write down will have metric. It will also have matter sector represented by the energy momentum tensor. But I cannot vary the metric to get this. So I need some auxiliary variables QA in it, which I can vary. Okay. There is a bit of at first sight you will notice that there is an issue. Normally in a variational principle, if I vary a degree of freedom QA, I get field equations for QA. You vary the A mu and you will get field equations for A mu. You vary J mu nu and you get field equations for G mu nu. But here we want to vary this QA but get equations for GA. So it has to be a very peculiar variational principle. Second, this must depend on TAB, but we have just no reason that if I add TAB to TAB plus a constant, the variational principle should not change. So how can I bring in TAB and at the same time keep it invariant under this transformation? It turns out that there is a very nice way you can answer both these and identify this QA. The point is that the variational principle should have a structure like this. You see, even though TAB is there, if I dot it with a null vector twice, then if I add to TAB a Kronecker delta times some constant, that Kronecker delta hitting a null vector because n square is 0 will not contribute. So TAB has to appear along with an auxiliary null vector field NA. And this of course we know now is the heat content, because I have told you that TAB, NA and B is essentially the heat density of matter. So you only add apples to apples and oranges to oranges. So whatever you add to it should be the heat density of gravity, which could depend on GAB and NA. So you must have a variational principle of this structure, and you vary it with respect to NA, but NA is an auxiliary variable, so this equation should hold for all NA at a given point. If that is the case, the equations of motion should have a structure like this. It's just a formal way of writing it. Because it has to be invariant under TAB going to a constant times Kronecker delta, there must be an arbitrary constant of integration in that equation, and you will have some geometrical object and its divergence should be 0 because the divergence of right hand side is 0.
If TAB is translated by a more general type of constant, some lambda AB, which is the constant that has been.
No, that won't work, because that is not what we need, because if you add to a Lagrangian, we can add only a constant. You see, even though I said the theory should be invariant under TAB going to TAB plus a Kronecker delta, That comes from the fact that you are adding a constant to a Lagrangian. So our primary symmetry transformation is addition of a constant to a Lagrangian. The crucial question is, can you find such a head? It is not at all obvious that such a variational principle will work. The remarkable thing is you can actually do that, and such a variational principle was known for quite some time. It was done in 2007, but now I am reformulating it in this language. The gravitational heat content has the form which is essentially quadratic in these null vectors, multiplied by a fourth rank tensor, and you need an extra constant with the dimensions of area purely for dimensional reasons. So I have introduced one more area dimension object into the theory. This PABCD should have a very specific structure. It should be a series of curvature tensors multiplied by a determinant tensor. In differential geometric language, is a wedge product of the curvature two forms. Okay, but this is the way it will be written down in composite. Now you go and vary this, and it turns out that the theory which you get is something which is known in literature. These are called Lanco's Lovelock models of gravity in arbitrary d dimension. Okay, so you can work everything out in d dimension, and the most down structure which you get, the geometry is Lanco's Lovelock theory. And a very special case of that is GR. In particular, if you say that the dimension is 4, then it uniquely leads to GR, and your field equations as this one, which is exactly the Einstein's equation with a lambda coming in as an integration constant. So that TAB going to a constant will just renormalize the value. So you have a variational principle which does that, but now we want to interpret it. So the question is, how do we interpret this Hg, the gravitational heat content, which now depends on xi and a null vector? Macroscopically, this Na is taken to be the null normal of the null surfaces. So you are just maximizing the heat content of all the null surfaces. Microscopically, I will interpret this as there is a x and an Na, and Na n square is 0, like something like a zero mass particle with a distribution function for the atoms of spacetime with a momentum n. Okay. So let me finish off the macroscopic part first. So here you identify this with the null normal, and you take this thing and integrate over the null surface, and this is the total heat density. If you extremize this, after extremizing, you can go and calculate what is its value. What is its value, the extremum value. And you find that this extremum value is actually given by this expression, which is just the heat density, where this is the local Unruh temperature, and this S is the walled entropy of the system, and it works for all the theories. Now, normally you think of the entropy as being proportional to the area. This statement is true only in Einstein's gravity. If you go to the more general class of theories, in particular this Lanco's Lovelock kind of theories, the entropy is a much more complicated expression, and it involves that PABCD which I told you. So as a result of which, it is non-trivial that you actually pick up this, no numerical factors, nothing, and that comes out very naturally. So this is what we are doing, and that explains the whole of this gravitational dynamics. Now let me go back to the statement I originally made, that Boltzmann said that if you can heat it, it must have microstructure. Now we have a thermodynamic principle to obtain Einstein's equation, so we should go and ask what are the underlying atoms of space and how many of them are there. Now we have this principle that if you want to store an energy delta E at a temperature T, you need this many degrees of freedom. The question is, since you can heat up the space-time, do we have a similar equipartition law for the microscopic degrees? Can you actually count the number of atoms? It turns out you can. And what you get is the following. This is the result which you are having. And this is also going to give meaning to the constant LP square which I introduced into the entropy. I just introduced it as a object with the dimensions of area. But what is its meaning? Its meanings come like this. One can show that if you take a region, I will show it figuratively in a minute, the bulk energy in a region which gravitates is equal to half kT for every degree of freedom. And how many degrees of freedom are there? In a small area dA, there is dA upon LP square degrees of freedom. So this is just the standard equipartition law between the bulk and the surface, and every area dA, you have dA upon LP square atoms associated. This is where the discretization comes in. It is not that you laticize it or you put a grid or you don't do any such thing. You are just counting. It is the counting which gives you the discretization, and to every area you associate the number of degrees of freedom, which is area upon LP square. So that identified LP square with a quantum of area in this circle, which is what appeared in the end. Let me try to show this in a somewhat nicer way. So this is a real space x, y, z at a given time, and you are looking at a region, just normal three-dimensional region bounded by a two-dimensional surface, which we take to be an equipotential surface. Now to this surface we associate a number of degrees of freedom, which is a upon LP square. There is a normal and there is an acceleration due to gravity. So you can have these observers who are feeling that acceleration due to gravity. But at every point I can also introduce a freely falling observer. So there is freely falling observer and this observer. And by comparing the two, I have a local Unruh Davis temperature G local upon 2 pi. Since it can vary from point to point, let me define an average temperature, which is the integral of this over this entire area divided by area. Now what I do is that I look at the energy which is inside. This is this total energy, magnitude of the energy. If there is an average temperature here, and if the matter has come to equipartition with that energy, which it might not have, but assuming matter has come to equipartition with that average temperature, I will be able to associate a certain number n bulk with it. This is just E upon it. Now if that equipartition holds in a static space-time, what one can show is that this n surface is equal to n bulk. This is what I told you earlier. So in all static geometries, you can show that this n bulk defined this way and this n surface defined this way are equal to n. Okay. So this is what I call holographic equipartition, with the word holographic used in the most primitive sense, that there is a correspondence between surface and bulk. There is also another result which comes from this, which is very satisfactory. The point is that it is a little bit incongruous to do all this and finally obtain Einstein's equation, which is what I did. I did write down Einstein's equation. But Einstein's equations are not thermodynamic. Einstein's equations are geometrical. But if gravity is a thermodynamic limit of something, then the gravitational field equation should not even be called field equation. It should be written as a thermodynamic law. Okay? And indeed you can do that. In order to do that, you have to introduce the two variables which I talked about yesterday, because I showed you that these two variables, where this is like the q, which is root minus g times symmetry, and this is its canonically conjugate momentum in the conventional approach, but it is just a combination of Christoffel symbols. It turns out that the q delta p and p delta q with suitable contraction of indices has a correspondence with s delta t and t delta. So there is a very natural thermodynamic interpretation to what you thought was metric and Christoffel symbol. So you can actually do this on another surface. So you have this correspondence, and using this correspondence you can interpret this quantity. You see this q delta p is going to be like s delta t. S is like the number of degrees of freedom. So n times delta t is like heating up of something. So that quantity, this is going to be a Lie derivative with respect to the normal to the hypersurface. This term you can show is equal to a term which is proportional to n surface minus n. What it is telling you is that the time evolution of the space-time, which can be thought of as either heating or cooling of the space-time, is driven by the deviation from the holographic equation. So there is an n surface and an n bulk, and the difference between them is what drives the time. This replaces the field equation of gravity. This is a single equation, but this has to hold for every surface, and that is equivalent to 10 Einstein's equation. So this implies and is implied by Einstein's equation. What it tells you is that Einstein's equation essentially captures how the difference between the surface and bulk degrees of freedom of a region leads to either heating or cooling of the region. So it is completely thermodynamics, and we just missed it, and we thought of it as a geometrical variable, and we have been trying to quantize it, and that is why none of the approaches had led to any success. Okay, there is also an interesting feature in the Newton's law of gravitation in this approach. We have introduced three constants. We introduced h cross, we introduced c, and we introduced a constant with a dimension of area. The h cross and c came from temperature, and Lp square came from the entropy. If you write down the Newtonian limit of the Einstein's equation, these are the only constants I have. The force law will become m1 m2 upon r square multiplied by this constant. Now you should resist the temptation to call this some other constant capital G as Newton did. Okay. The point is that the really fundamental constants which are independent of each other are Lp square, h cross and c. As a result of which, in this constant, if you take h cross going to 0 limit when Lp and c are finite, blows up on your case. This is important because it tells you that gravity, like matter, is intrinsically quantum and cannot exist when h cross going to 0. This is another major point of departure from all standard approaches. So let me explain that. The way we normally think of this is that there is a space and there is a time, but let us just concentrate on space. There is the space and you have an object kept on that space, like this slide changer. This object can be quantum mechanical, it can be classical, it can be relativistic, it can be quantum field theoretic, I don't care. But they all reside in space. If I take all the objects away, space remains. Now suppose I take h cross going to 0 limit. When h cross going to 0 limit, matter cannot exist because every atom in the matter will collapse. So all the matter will collapse, but the space will remain. This I think is a wrong approach. Space and matter are intrinsically intertwined with each other, and when h cross goes to 0, just like matter collapses, space also collapses. Space-time cannot exist as a classical entity, matter cannot exist as a classical entity. Space-time is intrinsically quantum gravitational or quantum mechanical. So the h cross coming here is something which is very gratifying. Now there is also one more thing. I will skip this because I don't have time to do this. Yeah. Now let me talk about the next part of the talk. So all these we have done at the macroscopic scale. So we introduced a null surface. The null surface has a heat density contributed by matter. It has a heat density contributed by gravity. You took the total heat density and you extremized it. And that gave you a set of equations which can be interpreted completely thermodynamically as a heating or cooling of a region of space-time due to the departure from the holographic equivalent. So everything was fine at that time. But in the process, in order to derive these field equations, we attributed a heat density to the geometry, and that involved a null vector, and we want to look deeper into it. What we want to do is to first of all understand the origin of this auxiliary null vector field. We also want to understand why null vectors are selected out, why not other kinds of vectors, and I want to determine the form of the heat density. Now the form of the heat density I wrote down was involving the derivatives of NE, but there is an equivalent form where it is simply RIB, NA, NB, and you have made it dimensionless by this, and that differs by a total divergence which does not contribute on a null surface. So we will concentrate on this form because it turns out to be simple, and it is also made dimensionless by multiplying by an element. The challenge now is to get this form of SD from a microscopic field, but we need to do this without knowing quantum theory of gravity. Okay, we don't have a quantum theory of gravity, we are doing a top-down approach, and we have to get there. In mathematical terms, we need to somehow recognize the discreteness and the counting or the combinatorics of the system, but yet use continuum method. So how do we do that? These two look mutually contradictory at the first look, but actually we have been doing this all along in fluid mechanics, but again it is never emphasized in that language, and that is why you don't see it like that. What happens is that if you take a fluid, just normal fluid mechanics, and you have a, let us say, water flowing, there are two levels of description for that. In the first level, you describe it with some Navier-Stokes equation and a continuity equation, etc. You use the density, you use the velocity field, etc. as the variable. What is a velocity field? At a given point in the flow of water, you attribute it a single velocity v, which is what it is moving. It is moving the mass in that velocity. At this level, you ignore velocity dispersion. This is a continuum description. You don't recognize the discreteness or atomic nature or molecular nature of water. But there is a deeper layer called kinetic theory, where you start from a distribution function, where you say that the number of molecules at a point xi with a force momentum pi in a phase volume is given by this expression. So here we are already recognizing discreteness because we are counting. We are saying how many number of particles. You don't do it in the continuum fluid mechanics. You do it in kinetic theory. But yet you use things like d3x. So if you read a textbook like Landau and Lifshitz fluid mechanics, he will tell you that this d3x is treated as infinitesimal for computational purposes, but physically that should be sufficiently large to contain large number of molecules. So you assume that such a scale exists, okay? And then you carry on from that. Now this xi has an extra attribute pi in that, which doesn't exist here. Okay, so you have an extra attribute which tells you that at a given point, suppose I have a glass of water and you look inside the glass of water at a given point, you can say that at this point there are several molecules of water, each having its own momentum, and it is the velocity dispersion or the momentum dispersion is what gives you temperature, because there is a random motion of molecules. So there are large number of molecules at a point. This at a point should be taken with a pinch of salt. So what we mean is that there is a small enough volume in which I can talk about large number of molecules with different values of pH. What we do is to translate all these into description of space. What I want to do is to think of a distribution function which is the number of atoms of space at a point xi with a momentum ni. So this at should be interpreted just like we do in fluid mechanics. So once you have got that, we would interpret the heating rate, which is, or the heat density which we have thought of, which is the heating rate per unit volume, as just the f of xi. This is what we want to do. Now what would this be? That is very easy, because you are just asking how many atoms of space are there in a region. It should be proportional to either the area or a volume of that region, because that is what makes the, it is the atoms of space which makes the space. So it could have been volume or area, and because of this holographic equivalence, any one of them would have been fine. So the mathematics has to tell us which one to use, and it does tell us. So you want to associate a volume or area with a point xi in this space. Here is where the problem comes, because if you try to associate it in a naive way, you will get zero. So some quantum gravitational input has to come in, and I will explain how it happens. So the way to associate a volume or area with a point is through what is known as equigeodesic surfaces. So let me explain what they are. They are actually very simple. So if you are in flat space-time, an equigeodesic surface is a sphere. We are looking at Euclidean space now. So you take some point and you send out geodesics in all directions for a length sigma. So since everything is flat, these are straight lines, and you go a distance sigma and you take all the points at that distance sigma, which is a sphere. So the equigeodesic surface is just a sphere, and the spacetime can be written with sigma as a radial coordinate, and sigma square times the metric on this surface, that will be S3 in 4 dimensions. Now if you take the square root of minus g, that will go as sigma cube, square root of h, which is the area element, that will also go as second. Okay. Which means that if I try to associate an area or a volume measure with this point, I have to take this equigeodesic surface, calculate the volume measure or area measure here, and then shrink this point sigma to 0. If I do that, both of them vanish, which is of course true. To a given point we associate 0 volume or 0 area in normal classical geometry. If you are in a curved space-time, things change slightly, but the fundamental result remains. In a curved space-time, geodesics will have some crazy shape, but you can still go a distance sigma in all these directions, and you can define this. and there will be a tangent vector at this point which is NE, and you can still write down the metric in this form, and it will now pick up curvature corrections. If you take root x, this is the point from which you are defining this surface has a root x, this region also has a root g, you will find that it is given by this formula. There is a correction because of the curvature at this point, okay, but this is Gauss. I mean, this is classical differential geometry where you know how, like if you take a surface of the sphere, yeah, take north pole and you send geodesics of a given length, you will be going along longitudes up to a point, then you draw the equigeodesic surface will be a latitudinal circle, and if you take its area or volume, pi r square or 2 pi r will not work because the earth surface is curved, and that correction is described by this. This is what we want. But you don't get it from here because again when I take sigma going to zero limit, this quantity is killed by this sigma. So you get zero. What we need is to introduce a 0 point length into the space-time. There is a huge amount of literature in the past which has suggested that one of the modifications of quantum gravity, this is the only input from quantum gravity, is to change the distance between any two events in space-time, sigma square, to some arbitrary function of this, but that arbitrary function has the property that when sigma goes to 0, it remains finite. So a simplest such function is sigma square plus L naught square. So whatever I am going to say hereafter works for an arbitrary function, but I will use this for simplification. So there is an equivalent description in terms of a dressed or renormalized metric. If you use the conventional language, you have a metric for which this sigma square was the geodesic distance between 2 points. Now you have modified this geodesic distance to this. You can ask whether there is another metric which I call the Q metric or quantum metric, which will now of course depend on 2 points, so it is not a local object, for which this is your geodesic interval. You can actually write down an expression for this which you will find in these papers. It's a bit complicated, but you can write down this expression, and once you have that expression, you can go and compute this root q and root c. What we will now do is to say that the number of atoms of space at xi with an attribute ni, it should scale as the volume or area measure of the equigeodesic surface, but in the quantum Euclidean space by taking x prime going to x. So what we are going to take is that this is proportional to either this or this, and we have to compute these two quantities. Now the interesting point is when you are taking sigma square going to 0 limit in the Euclidean space, I told you earlier, you are picking up null surfaces because sigma square equal to 0 is actually a null line. You are picking up null surfaces in the universe, which is exactly what you want. It is the null surfaces which are going to be horizon, etc., etc., and that idea comes about very naturally. When you do the computation, what you find is the following. This is the expression for the volume measure, this is the expression for the area measure. You will find that this just picks up the correction, sigma square becomes sigma square plus L naught square, sigma square plus L naught square. This is what you would have had even in the flat space time. The crucial difference is between these two. Here your sigma square just picked up an L naught square. Here there was an extra sigma which comes. Because of which, if I now take a sigma going to 0 limit, the volume measure still goes to 0. There is no volume associated with a point, but this remains finite. So you do get an area measure with this thing, which is just given by this, and this is precisely the quantity we are at. So this is also related to another fascinating result which we have been able to show recently, that whatever dimension of the space-time you start with, when you go towards Planck scale, the space-time behaves as though it is 2-dimensional. Okay? So this has been seen earlier in computer simulations in causal dynamical triangulations, etc., that the spectral dimension of the space-time goes to 2. Now we have a very general proof that this is how it comes about with a single input from quantum gravity, that there is a 0 point, which of course every model of quantum gravity has at some point. So once you have this, everything falls in place, and you can write down the expression for the distribution function, and you get distributed. What you wanted was this term, but you get it along with a 0 point contribution. So the mathematics tells you that there is a 0 point contribution, and that turns out to be crucial. What it tells you is that if you take the two-dimensional primitive structure of a sphere of radius LP square, it has an area 4 pi LP square, and the number of degrees of freedom per LP square is 1. So the total number of degrees of freedom you associated with it is 4 pi. Of course, when you say number, it has to be integer, so you can divide by 4 pi to redefine everything. You can define this, divide this by 4 pi, but essentially this is what we are talking about. So there is a 4 pi which comes out of this fundamental. This turns out to be very important. Now I will go back to the cosmological constant problem. In the conventional picture of our universe, there is a very strange combination of three states. What we believe is that all the observations in cosmology tells us that there is a very early inflationary phase existed in our universe, which is defined by a density which is rho inflation. Then there was a late time acceleration phase which we are now getting into, which is governed by a density associated with the cosmological constant. And in between there was a radiation and matter dominated phase, which can be specified in terms of another density rho. So in the conventional theory, conventional cosmological model, the Friedman equation can be written down entirely in terms of these three numbers. So there are three densities which are independent signatures of the universe, which describe the evolution. There is no relation between these three in conventional approach. What is more, so if you look at it, there is a region in which the size of the universe is like this, and then it increases, and then it goes flat. This is the inflationary phase, this is the late time acceleration phase. In both the times the Hubble radius remains constant, and in between it increases like this. Now the two of these three constants, like this rho inflation and this rho EQ, we hope that high energy physics will be able to tell us. So there are grand unified theory schemes which suggest that the inflation probably took place at 10 to the 15 GeV. Then there is a rho EQ which can be determined once these numbers are known, and that is of this order. However, we have absolutely no clue how to fix the third constant, rho lambda. In dimensionless units, it is going to be a number which is extraordinarily tiny, and this is what is usually called the cosmological constant problem. And many people believe that this is probably the most important problem in theoretical physics. In our way of looking at the universe, it turns out that there is an inflationary phase, there is this cosmological constant phase, and something is connecting it. And here, the n surface is equal to n bulk. They are approximately equal if the de Sitter phase is approximate, otherwise they are exactly equal. In between, n surface is not equal to n bulk, and the universe gets either heated or cooled the way I described it. What is more, in this particular approach, it turns out that there is a conserved quantity which remains invariant throughout all these phases. This is related to the total number of degrees of freedom associated with the geodesics which cross the Hubble radius. And you can actually determine this number. That is, you can determine this number in the sense that you can relate that number to cosmological parameters, these three constants. Now observationally we know these two, and we believe it is 10 to the 15 GeV. So you can go ahead and observationally determine what is the conserved quantity. If you do that, you find that that number is 4 pi to 3 decimal place seconds. This is purely from observation. But of course I don't want to take that point of view. I want to take the point of view that this number is fixed primordially at quantum gravitational state by the 0 point degree of freedom, which is 4 pi. So you plug that in, and using this I can relate these three densities, which cannot be related in the conventional system. When you do that, you get a beautiful formula. You find that the rho lambda can be written in terms of rho inflation and rho EQ with this form, multiplied by a very small number, exponential minus 36 pi. This is why rho lambda is very tiny. Of course, this is not 10 to the minus 123, it is much smaller than that, because this quantity is much larger than unity, and that gets compensated. Now, this is probably the most significant success of this formula. First of all, no model of quantum gravity has ever given a number. Okay, people are all running helter-skelter, and they are now even arguing that we will never give you a number. You should still call ourselves scientists. So that is in a pathetic state of affairs. So we first of all we get a number. Even a wrong number would have been good, but they don't even give you a wrong number. What is more, it gives the correct number in the sense that if you go and substitute these numbers, it will tally. Now, for biceps-like experiments which are going on, within a decade or so, we will nail down this number. Now, suppose it comes outside this band which I have predicted, then this theory is wrong. This model has a problem. There are no free parameters. You have only 4, 27 and 36 and things like that. There is nothing I can do to fudge it around. So this is a unique prediction. And if these values stay, then rho inflation has to be. Okay. So this is probably one message you should take from this talk, because this approach is producing something which you could not get from any other approach, and it solves. It has the potentiality of solving in terms of relating these things, which was not relatable in other approaches. Now, there is a little bit of speculation, which I'll just do it in 1 minute. What is possible is that once you have a distribution function for a system, you can do something more. You can convert it into a probability, like there's a standard way of doing that. And then you can sort of think of NA, NB as some correlator, which is RAB inverse. If you have a probability distribution for NA, NB, such that the correlator is the matrix inverse of RA, then the natural way in which the field equations will be written in this approach is something like either quantum or stochastic average of TAB multiplied by the probabilistic average of NAB is equal to 1. Okay? This TAB should be actually interpreted as T bar A, that is TAB minus half DAB T. There is a typo here. But you get an equation which is broadly of this kind. This equation has a Machian kind of interpretation. What it tells you is that if I put TAB equal to 0, I get 0 equals 1, which is wrong. Therefore, it tells you that geometry and matter has to come together, and you cannot think of geometry without matter. This is important because we have always thought of cosmology as a part of general relativity. The way we do this is that you start from GR, then you take various special solutions. One solution is a short-scale metric, and another solution is Friedman-Robertson-Walker, and you use Friedman-Robertson-Walker to describe the universe, and it has been very successful. But if GR is not the ultimate end, and GR is a thermodynamic limit of some atoms of space, then you have to ask whether the thermodynamic limit has been achieved. In almost every system we know that thermodynamic limit has some limitations. Like it could happen that the time scales or space scales etc. is not good enough. And this can happen at the outer fringes of our universe. So it is possible that when you are discussing super Hubble scales of the universe, you should not first take the statistical mechanics, take the thermodynamic limit and use thermodynamic limit to describe it. You should actually go to the statistical mechanics and ask whether the thermodynamic limit has been reached or not, which means there could be correction to cosmological prediction coming from this model. And the fact that it relates cosmological constant to inflation, or the fact that it gives you an equation like this, or the first hint that there is something interesting happening. So what are the open questions? The most important open question is, where does the matter energy momentum tensor fit in this complete scheme? So I had just assumed that is a matter energy momentum tensor, and I described the geometry. So geometry part is beautiful, but matter is still there. And the entire picture, as I told you that everything is quantum mechanical, both space-time and matter, tells you that matter and geometry has emerged together in a very natural way. We don't know how to do this. We also have to combine the action extremum for matter, which is what you normally do, with an entropy extremum for gravity. This can be done possibly using Euclidean approach. Then you can also write down an evolution equation for this when things are not in equilibrium, and we need an interpretation for that. And we need to know how to generalize these to Laplace level of models. So just to summarize, if we demand that the gravity is immune to zero level of energy density, you are forced into a variational principle with an auxiliary null vector, which is very nice. This variational principle, the geometrical variables in it, and the evolution equation, all of them has a thermodynamic interpretation at the macroscopic scale, with Ni identified with the normal Fresnel vectors. If I take the number of atoms of space-time at a given point associated with a point to be proportional to the area measure of the space-time after introducing a 0 point length, then we do get this correct variation principle. And a Planck scale 2 sphere has 4 pi degrees of freedom, and using that you can determine the value of the cosmological, which I think is the most important feature. That usually people say that you cannot expect quantum gravity to make predictions. That is just because we are not clever enough. Okay. There are always low energy relics of a beautiful theory, and that has to come. And this, I believe, is the first example that quantum gravity, or putting principles of quantum theory and gravity together, can actually lead to testable predictions in cosmology. Thank you.
Perhaps we can also capture all the questions.
Area becomes fine, but the volume will change.
That's correct.
The area is LP square, that is Planck square.
No, area is not LP square. The area measure, that is when you write down, how do you compute area? You compute area by taking some square root of h and integrating over the coordinates. What happens is that the square root of h picks up, this is what happens. The area measure at a distance L0 has this L0, then this is the angular part, and it picks up this correction term. It is not just L0 square or L0 cubed or something. There is this correction coming. That's finite. Yeah.
By this idea, can we solve the difference formula?
Yes. In principle, I didn't talk about singularity at all. What we believe is that the moment you have introduced a 0 point length into the space-time, you cannot ever talk about a singularity, because singularity assumes that you are going to a point, but uncertainty principle prevents you from going anywhere smaller than Planck length square, which means that at the Big Bang singularity as well as inside the black hole singularity, you have to have some kind of a bounces or some dynamics as T. But that cannot be handled by this formula, because in this formalism it is like you start from the flow of water described by fluid mechanics. Then you describe flow of water in terms of the number of molecules at a given point by doing kinetic theory. But there is a deeper layer of description where each molecule has to be written, a Schrodinger equation has to be written down for each molecule. We haven't reached that. So from the kinetic theory approach alone, whether you can solve, you can sort of make a conjecture that the singularity will be avoided. But what you really want to know is that what replaces the singularity. I am not sure we can do it with this level. We are trying to do a few things, but I don't have any hard results on that.
Any further comments? Can you please show the slide on open questions?
Oh, open question.
I mean, how do you interpret this evolution of F? Now, you gave this analogy with the description of fluid dynamics. I think that was basically the Euler and the Lagrange description, and you are perhaps following the Lagrange description.
No, you can take two levels. First level is that if you take a mean velocity, mean density, then you can write it down either in the Eulerian coordinates in terms of continuity equation and the Navier-Stokes equation, or you can go to a Lagrangian description and do that.
Right.
But in neither of them you are allowing for velocity dispersion. So the description which I am following is that of Boltzmann. You have a distribution function. You say df by dt plus v dot del phi plus gradient of phi is equal to the collision term. So this is the evolution equation for the distribution function which I am. So you can write down that evolution equation.
You can write down that.
I can write it down because I know what it is. So you can write it down, but the important thing is to interpret it.
But can't you recast it in the language of the more familiar, say, Eulerian description?
No, you can't, because the Eulerian description and the Lagrangian description kills the velocity dispersion. You see, let me emphasize that. Suppose you write down the standard equation which you will have in fluid mechanics, you need by dT plus or is equal to some gradient of V by rho plus other forces, etc. What is this V? This V is obtained by taking a distribution function x, comma, let me call this u to distribute from this V. Then you put u here, then you do an integral d3 u. This will be a function of x alone. Of course, if this has t in it, then it will be a function of x and t. So this is the mean value of all the velocities at that point, which is captured by this. But what about this v square? This is ignored. And that is what gives you the temperature. And at this level of description, you have to give an equation of state between P and rho and introduce the temperature. So in contrast, you have a description where you have dF by dt plus V dot, or rather in this notation I should write u dot del F minus gradient of any potential dot dF by du is equal to the collision term in it. This is the Boltzmann's evolution equation for the distribution function. This is a deeper layer of description compared to this. So I can go from here to here by taking moments, but I cannot go from here to here. This is not possible. So that is why if I go and write it down in terms of these languages, which you can, and you will get a Navier-Stokes equation. Okay, so that slide, that is one of the slides which I skipped. If you go back, this is actually a work done with Sumata Chakravarti, recent 2 papers. We can actually show that there is a gravitational momentum attributed to a space-time, and when you take these projections, you are essentially killing all the velocity dispersion, and you will end up getting a Navier-Stokes equation on the null surface. That you do get. Okay, but this was known. This was known as early as 2010. Okay, but from this, I could not have gone to this. So you needed some other deeper idea here to come back. That is what.
The other general question, I mean, you have tried to interpret this gravity as some thermodynamics.
Right.
Now, so since you have these different theories of gravity,
correct.
So what happens? You have these different ways of taking the limit, or
no? The different theories of gravity in this approach tells you how space-time evolves differently. So what does gravity do? It tells you the evolution of space-time. Now, different theories of gravity attribute different evolutionary histories to the space-time. The dynamics of the space-time is what is different in different theories of gravity. This is just like saying that if I have a glass of milk and a metal rod, the dynamical description of these has to differ. And for that I need to know the entropy. So if you give me the heat density or the entropy, that Hg which I wrote down for a theory, then I know what the theory is. Now the Hg has a simple natural form for all Lancos Lovelock models of gravity. If you take some other kind of theory, so I can construct any Lancos Lovelock model of gravity very naturally in the thermodynamics by changing the form of the entropy. But if you take some other crazy theory like F of R gravity, then you can actually twist things around and write a complicated expression. But it is very clear that no one would have written out that expression unless that theory has been given. So the form of the entropy function will become very complicated.
So this is the main question which I am trying to come at. I mean, do you have some sort of a theorem, or do you know that you can always, by this choice of entropy or whatever it is, come down to the theory of gravity?
You can do that. So somebody has done it long back. In 2008 or something, a Chinese group did that generalization. But when you do that, then the form of the entropy density, I can send you the reference. There is an work which starts from the equation of motion and writes it down.
And one last thing was that at the intermediate stage you wrote this how the metric has changed. The GAB you replace with GAB plus some UAB. You had a
QAB?
yes, QAB.
Q is the quantum metric.
Quantum metric. Yeah, I think, yes.
Yeah.
And, right. Now, can you interpret this in the following way? I mean, you start from some unrenormalized G,
Correct.
and
And
then you have a renormalized K.
absolutely, that is
But then, of course, you could interpret this as a loop correction.
that doesn't work. Okay, so I get what you are talking about. We do give that interpretation in this paper. So the way we talk about this is the following. If you take, say, lambda 54 theory, and if you do the renormalization up to 2 loops, then I know that not only lambda and the mass, coupling constant and mass get renormalized, but even field gets renormalized. Same with QED. We know that the field gets renormalized. So in a conventional approach, if you start with a metric as my field, and I do quantum gravity, then the metric has to get renormalized. The problem is that if you do perturbative loop renormalization, you will never capture this picture. The form of this metric tells you that it is completely non-perturbative. And if you take x going to x prime with a finite L0, it blows up. That is, the metric is infinite at all points. Okay? And it has a meaning only when you smear it over a particular length or something. That doesn't affect us because we are only going to use this to get the volume and area measure. So I can take this and then take the limit, and when you do that, it gives you a finite result. So it's an intermediate tool which can be used to get finite results in the end. But if you try to interpret QAB itself as a corrected metric, like people have done, written down effective equations and calculated quantum correction to GAB, etc., you can't interpret it like that because this result is completely non-perturbative.
Yeah, I have a couple of questions, and one of them is that whenever you talk about atomic pictures of thermodynamics,
Right.
you have to have two scales, right? One is the atomic scale, and the other one where sort of temperature effects begin to be seen, like a
Okay.
kinetic theory scale. So here the atomic scale is like the 0-point length.
Right.
So what is the kinetic theory scale?
Okay. Now it turns out here is that you don't really need a kinetic energy scale here. It turns out there is only one scale in this problem, which is L0. What happens is that what we call the mesoscopic scales in this paper. This is something when you are working at the limit of, let us say, 100 Planck length or 1000 Planck. So it is only a numerical factor. So it is not that there is one scale where thermodynamics works and at another scale this thing comes in. So let me try to give you an analogy in normal condensed matter physics. So if you take a lattice of atoms and or a gas, take a gas made out of molecules. Now there are two scales here. One is the intermolecular spacing, which comes from the density of particles. The other is the actual size of the atom, which comes from the internal Schrodinger equation or the dynamics. Now this is the second scale, the first scale, the intermolecular separation, is what you have been talking about as a thermodynamic scale, because only when I can coarse grain over scales much bigger than the intermolecular separation that you do get a thermodynamic. But here I cannot place atoms of space in space at different lengths. You understand? There is no such thing as an interatomic spacing of the atoms of space.
That is why I am asking.
Therefore, I do not have a second scale. And the second scale is set by, in a continuous form, if you try to approach Planck length, if you are 1000 Planck length and 100 Planck length and 50 Planck length, your predictions will be accurate at that order. So there is no two separate scales, and you cannot have two separate scales because of this reason which I explained to you. You cannot take atoms of space and put it in some other space and ask what is the interatomic spacings of the atoms of space. That doesn't make sense.
Okay, I'll think about that. So the other question is, when you talk about entropy and then you go to this general relativity,
Right.
do you start with time-space separation? Do you have
No, it's completely covariant.
but your entropy should determine which is the direction of time evolution?
No, not really. Because this entropy which we are talking about here finally lead to Einstein's equation.
Right.
Einstein's equations are invariant under t going to minus t.
Yes.
Okay, so it does not fix the time evolution. So we spend a lot of time trying to understand whether the n surface minus n bulk equal to heating, that sign there has any meaning, etc. But it doesn't have a meaning. So that issue as to whether the entropy has to fix, this is a major philosophical issue, whether it does or not. This is more like a microscopic entropy which we are talking about. So it doesn't fix our time direction at all.
Nice. And the last question is, you talked about shifting the Lagrangian by a constant. In your case, that will shift the action by infinity, right?
In any case, right?
In any
case, if you
right.
Yeah.
So
But you have to always think of a bounded region in which the action is defined.
But then you will have boundary effects.
No, if you have a boundary in any well-defined theory, like even in gravity, you can always think of an action in a bounded region B, and then go and calculate what are the boundary terms which need to be added in order to correct that. And they can be taken into account. There is no issue there. But actually I don't need to do that because I can work equivalently in the Lagrangian formulation. Suppose I just take a Lagrangian, I have two Lagrangians which differ by a constant. Okay? And then I go and ask if these two differ by a constant, what does TAB do? And I can translate my symmetry in terms of the stress tensor, which is what I did. And I can work entirely with the local. So that problem is nothing special to this approach. Whenever you write down an action, you have to be careful about what happens at the boundary.
So if there are no further questions.
You have a question? Yeah, right.
Can you write down any other fluid mechanics equation rather than Navier-Stokes equation? I mean, Bernoulli's equation or Euler's equation?
Right. Well, Euler's equation you can get as a limit of Navier-Stokes equation where the viscous coefficient goes to 0.
Exactly. But there is a problem because Euler's equation is hyperbolic in nature.
Right.
So space-time cannot be hyperbolic.
No, it is not the space-time. The variables in which this Navier-Stokes equation would be returned takes care of that transformation. So these variables do not actually have a very nice interpretation. See, the reason we went to this distribution function and the reason I was telling him that I discourage working at the Euler this thing is that I wrote down a velocity. Now you can go and ask what is this velocity? I mean, what is moving? Okay, and it turns out that it is just a geometrical variable, some combinations of Christoffel symbols. It does not have a nice interpretation. But the distribution function F has a very nice interpretation in terms of the number of atoms of space in a given form. So the short answer to your question is that you get Navier-Stokes equation in a natural way, but the interpretation of the dynamical variable in the Navier-Stokes equation is a bit suspicious. It seems to be just a mathematical anomaly. But the distribution function is much better.
Because for evolution you need some gradients and you have to...
Yeah, the gradients do come about.
Yeah.
The gradients are defined as Lie transport terms in the background.
So if there are no further questions or comments, let us thank the speaker, Professor Padmanabhan, Actually, I mean, apart from being really a brilliant researcher, he's also an exceptional teacher, as you can see. I mean, the number of students has not dwindled. I mean, there's...
Yeah, but they are not asking questions.
They are a bit shy, they're asking later. But I'll just give a small anecdote. I mean, I was reading a biography on Newton, and this is very revealing. So Newton was asked to take a course at Cambridge. So of course Newton being Newton, so everybody knows, so the class was completely filled. However, after a few classes, the number of students slowly started to dwindle. At one point, and that was only when Newton had, I mean, he had to take about 20 lectures. So after 5 lectures, there was not a single student. However, Newton being Newton, he was so he came and took the class. He took all 20. I mean, there was not a single student, but he told the authorities, I have taken full 20 lectures. So you have to pay me for that. Whether there is a student or not, I don't know. So, of course, I mean, but you can see what the case of Patty, the number is conserved. It has not changed. So we thank you very much, Professor Padmanabhan. And we do wish that sometime in the future we can again visit our center and our city also. Thanks a lot.